Good day. I am here to present my project titled Major Depressive Disorder Detection Using Effective Connectivity of Resting State EEG Signals and a 2D Convolutional Neural Network. This project explores the application of advanced computational techniques to enhance the accuracy of mental health diagnostics. In this presentation, I will outline the introduction, methodology, result, and findings of this research. To begin, I will provide some background on this study. This project focuses on major depressive disorder, MDD, a mental health condition characterized by persistent low mood, low self-esteem, and loss of interest in activities. MDD is a leading cause of functional impairment worldwide, requiring long-term clinical management. Current diagnostic tools rely on questionnaires and psychiatric evaluations, which can be subjective and prone to inaccuracies. Since brain disorders are linked to abnormal brain structures, this study uses effective connectivity, EC, to represent the interactions between brain regions. By converting EC data into images, a 2D convolutional neural network, 2D CNN, was developed to classify MDD with greater accuracy. Currently, the absence of clinically approved biomarkers for major depressive disorder, MDD, means its diagnosis relies heavily on subjective diagnostic criteria. To address this, computer-aided signal processing is crucial for distinguishing MDD patients from healthy controls, HC. Effective connectivity, EC, provides valuable information about the influence brain regions exert on one another. Given the graph-structured nature of EC, integrating it with a 2D convolutional neural network, 2D CNN, holds potential for improved classification of neurological conditions. The problem this project seeks to address is, how effectively does EC capture the features of MDD, and can it achieve a diagnostic accuracy of over 95%? The significance of this work lies in exploring alternative diagnostic methods for MDD, contributing to advancements in mental health diagnostics. The primary objective of this project is to develop and evaluate an EEG-based classification algorithm that utilizes EC matrices and 2D CNN to identify MDD. This project focuses on the following areas: subjects of interest, major depressive disorder, electroencephalography, effective connectivity within the default mode network, resting state EEG signals, and 2D convolutional neural networks. Tools: MATLAB for data processing and algorithm development. Deliverables: development of the classification algorithm, training and testing of the algorithm to evaluate its performance. This scope ensures a focused approach to achieving accurate classification of MDD using advanced signal processing and machine learning techniques. For methodology, this study utilizes the following tools, dataset, and architecture. Tools: MATLAB R 2022b. MathWorks Deep Learning Toolbox, GoogleNet. Dataset: the data was sourced from Hospital University Sains Malaysia, HUSM. Healthy controls, ICEESE data from 30 age-matched individuals, male. Equals 1911. MDD patients. Data from 30 patients diagnosed using DSM-4 criteria, excluding comorbid psychotic symptoms. These tools and dataset form the foundation for the proposed methodology, focusing on the classification of MDD using advanced signal processing and deep learning techniques. The development of an algorithm for automated MDD diagnosis using brain-effective connectivity from EEG signals involves the following steps: EEG data collection and pre-processing. 19-channel EEG signals were recorded at 256 Hz with bandpass, 0.1 to 70 Hz, and 50 Hz notch filters applied. Artifact removal was performed using EGLab, and data were segmented into 2-second windows. PDC matrix calculation. Partial directed coherence, PDC, based on the MVR model, was used to calculate the connectivity matrix, 19 by 19 by 64, from EEG signals. DMN connectivity extraction. The PDC matrix was processed to extract effective connectivity data mapped to the default mode network, DMN electrodes. Conversion to adjacency matrix. EC matrices were converted into adjacency matrices for input into a 2D convolutional neural network, 2D CNN. 2D CNN training and classification. The dataset was split into training, validation, and testing subsets, 80 hours, 10 minutes, and 10 seconds ratio. Training was performed on a GPU, and the model was tested with data from unseen subjects. Performance evaluation. Classification performance was evaluated using accuracy, PPV, sensitivity, specificity, and the confusion matrix to distinguish between MDD and HC subjects. This methodology uses PDC and 2D CNN to accurately classify MDD, contributing to the development of automated diagnostic tools. Results and findings. This section presents the results of the project, divided into 3 approaches: sample-based, subject-based, and frequency-based, using SVM. The dataset included 30 healthy control, HC, subjects, 4,030 samples, and 30 MDD subjects, 3,708 samples, ensuring a balanced dataset for evaluating the 2D CNN performance. The 2D CNN consists of 3 convolutional layers: batch normalization, ReLU activations, a global average pooling layer, a dropout layer, and a fully connected layer for binary classification. The frequency-based approach uses SVM. The model was trained using data from the selected subjects and tested on unseen subjects. Performance was evaluated using accuracy, precision, sensitivity, and specificity. Using the sample-based approach, the trained model achieved 98.24% accuracy in classifying MDD with EC of resting state EEG signals and 2D CNN, surpassing the 95% target. The positive predictive value, PPV, was 97.78%, sensitivity was 99.6%, and specificity was 95.58%. The network achieved a validation accuracy of 94.45% within 10 epochs, with a training time of 25 minutes 48 seconds. The process involved 14 10 iterations. The learning rate was set to 0.0001 with a constant schedule. The confusion matrix shows that the 2D CNN model achieved an accuracy of 98.24% in classifying MDD and HC samples, demonstrating high accuracy in identification. In the subject-based testing, data from 30 HC and 30 MDD subjects were organized into training and testing folders. The 2D CNN model was evaluated on each subject's data to assess its classification performance. As summarized in the table, the model achieved an average accuracy of 98.07%, with precision, PPV, at 96.49%, sensitivity at 99.7%, and specificity at 96.44%. MDD classification performance. For MDD subjects, subject 1 to 15, the model achieved high accuracy, ranging from 92% to 100%, effectively classifying most PDC matrices as MDD. As shown in the table, the model's final decisions align with these results, confirming the success of the subject-based approach. An SVM model was implemented as an alternative to the 2D CNN, using frequency-based data with 64 bins to classify MDD and HC subjects. The model achieved 90.9% accuracy, with precision, PPV, at 92.63%, sensitivity at 97.39%, and specificity at 94.84%. An SVM model using 64-bin frequency data was implemented as an alternative to the 2D CNN for classifying MDD and HC subjects. The TSNE scatter plot visually illustrates distinct clustering of MDD and HC subjects, highlighting the separability of the two classes and providing insights into the underlying patterns within the dataset. Result of overall development. The table highlights the strong performance of the proposed MDD diagnosis algorithm across 3 approaches, demonstrating its robustness and reliability as a promising tool for early and accurate MDD detection. In conclusion, the accurate classification achieved by the 2D CNN model supports the development of a reliable diagnostic tool. This study highlights the potential of effective connectivity, EC, as a valuable biomarker for MDD identification, contributing to improved mental health diagnosis and treatment while advancing understanding of this complex condition. Thank you for watching.